This is Dr. John Bergduff. In this video, we're going to do an example involving probability, and in particular, we're going to be looking at what is meant by a multistage experiment, and we're going to solve this problem using tree diagrams and along the way illustrating the concept of conditional probability. So let's get started. A box contains 5 red balls, 3 white balls, and 1 green ball. You draw out 1 ball, put it back, and draw out another ball. What is the probability of each outcome? So as we work this problem, we're going to assume that at any given time, any one ball in the box is equally likely to be drawn as any other ball. And the type of outcome we're talking about in the question, if there's basically 2 draws, you'd end up with 2 balls, whatever ball you picked out first and whatever ball you picked out second. So there's a number of different outcomes. A very good way to illustrate the outcomes is indeed to draw a tree diagram. And what you do is this. You imagine that you're thinking about what can happen on the first draw. And the first ball that you draw out could be one of 3 things. It could be red. I'll just abbreviate that with R. It could be white, or it could be green. So the branches of the tree illustrate what can happen with the first draw. On the branches, I'm going to write the probability of each. Now let's think about this. If we have 5 red balls, 3 white balls, and 1 green ball, 5 plus 3 is 8, plus 1 is 9. So there's a total of 9 balls. If 5 of them are red, then the probability of drawing a red ball would be 5 out of 9, 5/9. The probability of drawing a white would be 3 out of 9, 3/9. And in general, it's probably best to simplify the fractions as you go. So 3/9 reduces to 1/3. And finally, the probability of drawing a green ball is 1 out of 9, 1/9. So I'm going to write the probability of drawing a green ball right here. After you draw the first ball, then you draw a second ball, and you could draw any one of these colors no matter what your first ball was. So your first ball could be a red, and then your second ball could be red, white, or green, and I'll represent that. See, the tree is branching out here. If the first ball is white, the second ball could again be red, white, or green, following the branches here. And then finally, if the first ball is red, the second ball could be again red, white, or green. Let's draw these probabilities on here as well. And they're going to be the same because after the first draw, you put the ball back and the box contains exactly what it had before. So the probabilities, again, are going to be 5/9, 1/3, and 1/9 in all scenarios. 5/9, I'll kind of write that like that because I'm a little cramped. 1/3, 1/9. 5/9, 1/3, 1/9. The tree diagram illustrates that the outcomes that you would have would be, for example, I represent them this way, a red on the first draw and a red on the second draw. That's the top branch of the tree. What would the probability of that? Well, in a multi-stage experiment, the probability of the combined result, one followed by the other, is simply the product of the probabilities along the branches of the tree leading to that outcome. 5/9 times 5/9. And that would be 25 over 81. Similarly, the probability of a red followed by a white would be 5/9 times 1/3, and that's 5 over 27. This is going to give me all the fractions in reduced form, I believe. You could also have a red followed by a green, and that would be 5/9 times 1/9, multiplying the probabilities along the path or the branch that leads from through red and then finally green. 5/9 times 1/9 is 5/81. Continuing on, we could have a white followed by a red, and that probability is 1/3 times 5/9, or 5/27. A white followed by a white, that's 1/3 times 1/3, or 1/9. A white followed by a green, and that probability would be 1/3 times 1/9, or 1/27. Finally, green times a red would be 1/9 times 5/9, and that's 5/81. A green followed by a white would be 1/9 times 1/3, and that's 1/27. And a green followed by a green would be 1/9 times 1/9 equals 1/81. The probability of one event followed by the other is simply the product of the probabilities of the events. So you follow the branches of the trees and multiply those probabilities, and that gives you the probability of every possible outcome. Let's switch this up just a little bit. So the key, or a key thing about this particular question I did, is that after the first draw, you put the ball back. What if you don't? A box contains 5 red balls, 3 white balls, and 1 green ball. That's the same as last time. You draw out one ball, but you don't put it back, and then you draw out another ball. What is the probability of each outcome? Well, that's going to change up my diagram a little bit, but I can still draw a tree. I'm going to think about the first draw and the second draw. And at each case, at the beginning, at least for the first draw, I could pick out a red or a white or a green. And the probabilities in this first draw would be exactly what they were in the way I did it before. There's still 9 balls. 5 out of 9 are red, so the probability of red is 5/9. 3 out of 9 white balls, so that is 3/9, which again reduces to 1/3, so nothing is changing so far. And then 1 out of 9 green balls, so that's 1/9, and that doesn't reduce. When you draw out the second ball, you can still, if the first ball is red, you could draw out a red, a white, or a green. This might get a little cramped here. We'll have to see. But something is different. Because my first ball that I drew out was red, I don't have 5 red balls anymore. I only have 4 of them. And more importantly, perhaps, or equally important maybe, is I no longer even have 9 balls. The fact that I started with 9 balls and took one out and didn't put it back means that there's now only 8 balls, and only 4 of them are red. So the probability of a red followed by a red is 4/8, which reduces to 1/2. Now, what this is a wonderful example of a conditional probability. The probability of a second thing in a sequence happening may very well be influenced by what happened the first time. And the probability of the second occurrence might be conditional on the probability of the first occurrence. That's exactly what happens here. I've changed the scenario, and so the probabilities are no longer the same. They're dependent or conditional upon what happened first. So let's look at the other scenarios that are possible. You have a red followed by a white followed by a green. You've taken one ball out, so there's only 8 balls, but the first ball that I took out was a red one. So I have all the white balls left, which means the probability would be 3/8. And for the green ball, well, there's only 8 balls, but if I took out the red one first, that green ball is still there. It would now be 1/8. So those are the options that you could have if your first ball is red. Now, if the first ball is white, the second ball could be red, white, or green. I may regret spreading that out quite so much. Let me fix that a little bit. There we go. Red, white, or green. And let's think about what happens here. So we have, again, a conditional probability. We've had a first step where we've taken out a white ball. We started with 9 balls. Now we only have 8. But if the first ball we took out was white, then all the red balls are still there, and that would give me a probability of 5 out of 8. However, in the second case, I've drawn out the white ball, so not only is it the fact that there's only 8 balls altogether, we have 1 fewer white ball. So there's only 2 balls out of 8, 2 white balls out of 8, or 2 8s, and that will reduce to 1/4. And then as far as the green balls are concerned, you've only got 8 balls, but since you took out the white ball, you haven't affected the number of green balls, and that's going to be 1 out of 8. Now, when we get to the final stage, we have to notice something interesting here. If the first ball that I took out was green, and there's only 1 green ball, then the only options you're going to have for the second stage or the second draw at that last case is green followed by red and green followed by white. You're not going to be able to get green followed by green because there's only 1 green ball. We do only have 8 balls, but all 5 of the red balls are still there, so this probability is 5 8s. And the probability of a green followed by a white is 3 out of 8 because all 8 white balls are there. So if I make a list of all possible outcomes, I could have a red followed by a red, and the probability of that I would get by looking down the branch of the tree that goes to red and then to red, and that would the product of those probabilities would be 5/9 times 1/2. So that probability would be 5/18. I could also have red followed by white. The probabilities along that branch of the tree is 5/9 times 3 8s. And 5/9 times 3 8s, I could reduce that a little bit. I think I will. Notice that the 3 divides into the 9 3 times, so that the product will be more simply 5/24. So that's not so bad. Then we could also have a red followed by a green, and tracing down the probability tree there, we would have 5/9 times 1/8. Okay, nothing simplifies there, so that would be 5/72. Then I would also have the possibility, or the outcome, white followed by red. That would be, tracing down this branch of the tree, white followed by red, 1/3 times 5 8s. And that would give me 5/24. Notice you do have some repeated values here. That will happen. You could have a white followed by a white. That would be 1/3 times 1/4. Going down that branch of the tree, that's 1/12. White followed by green, 1/3 times 1/8, which would be 1/24. And then we have, going to the branch of this tree, green followed by red. Green followed by red would be 1/9 times 5 8s. And that's 5/72. And one last option, because there is no green option, 1/9 times 3 8s is equal to 3. Oh, no. We can divide the 3 into the 9. That's a good thing. So that would then be 1 on the top, over 3 times 8 is 24. 1/24. So we definitely want to reduce those fractions if we can. So this is using a tree diagram, and it illustrates a multi-stage experiment, and it also illustrates the idea of conditional probability, where the second event is influenced by the first or conditional upon it. I'm going to do one follow-up question based on this chart that you see right here. So going to another screen, in the scenario where the first ball is not replaced before the second ball is drawn, what is the probability of drawing two balls of the same color? So we're going to have to look back at this, but remember we had red balls, white balls, and green balls, but there's only one green ball. The only way you could get two balls of the same color would be if you had a red followed by a red, or a white followed by a white. Let's look back and see what those individual probabilities are. So let's find them. A red followed by a red, that's right here. That probability is 5 over 18. So let's write that down. And then a white followed by white, that probability is right here, 1 over 12. So what would the probability of drawing either of those be? Well, what you do there is you simply add these two fractions together, 5 over 18 plus 1 over 12. Guess what? That gives us a scenario where we have to find a common denominator. We never get away from that, it seems. The least common multiple of 18 and 12 would be 36. What I would need to do is need to take the 5 over 18, and to get a denominator of 36, I'd need to multiply numerator and denominator by 2. And to do the same thing with 1 over 12, I'd need to multiply numerator and denominator by 3. So I end up with 10 over 36 plus 3 over 36, and adding those together gives me 13 over 36. And that's a nice example of probability, multi-stage experiments, conditional probabilities using tree diagrams. Hope that was helpful.